All right, so now we'll make fun of Aiden with his gaming the other night. So Aiden over here was playing Dungeons and Dragons in VR with us. And if you've never played D&D, it's a tabletop role-playing game type thing, but this is completely in VR, but it's still the same type of turn-based thing where you and like three other people are like, you're deciding what to do each turn. So you kind of talk through, it's like, okay, you're gonna zap this person, then you're gonna move over here afterwards. So there's like a debate. Well, whatever we started talking about, he would just do it, regardless of how like good of an idea. And we're going to connect this to this class because we're going to talk about an algorithm is what happened. So he would just do it, and almost always it was a bad idea.
Okay. I don't think that's fair.
Almost always was a bad idea. So he would just do it. And he also had a habit. I mean, so he was playing this wizard guy. He's supposed to be back out of the way, like not in harm's way. And he decided that what he had to do any of his moves was always move right into the action and then cast his spell, leaving him stuck in the action. So we had implemented a rule called the 8-second rule. It was an algorithm that he had to wait 8 seconds before doing any sort of move. That way we could all get the rest of our thoughts out. So that was the problem. That was this 8-second algorithm thing. But then we had the issue when he seemingly gave his controllers to his cats or whatever else is happening.
Okay, so to explain it, I was talking to my roommate, so I was a little distracted. He just came back, so that's what happened.
We were all dying. We're sitting there dying. We needed him to resurrect one of us. And what does he do? I mean, we're like on death's door. So he hits the spider eggs, bringing 2 more spiders into the scene. That's all we needed right then, is more enemies.
Interacting, though. We did it.
We barely survived that level with our lives.
I promise you all that
We were 1 move away from exiting that level of the dungeon, and all of a sudden now we're on death's door because his cat has his controllers. But that's what makes Dungeons and Dragons fun, is stuff like that.
Your cat had to control it.
That's what it seemed like.
Oh, okay.
It seemed like he was, and when it was his move, when we needed him to like resurrect somebody and heal them, he was doing everything but that. That was not part of what his play style was in that moment.
Gotcha.
Main tank is down. Let's bring more spiders in, and then put myself in harm's way. It's complete, it's complete garbage. All right, so let's look at, let me make sure I have the recording started. Yep, I do. So homework for today: write a function that takes an array and its length as parameters and returns a new array that is the original in reverse, right? So we're building a brand new array. Well, let's just go in and write this. And let's see, what do we got here? Yeah, this is us stuff. Okay, so we're going to go ahead. We'll prototype this guy. Now, what does the function say to do? It says we're going to take an array and its length as parameters, and we're going to return an array that is the original in reverse. All right, so we're going to be returning a new array. So our return type is going to be an int array. We'll call this guy reverse array. He'll take in an int array as a parameter and an int length. That is, it takes an array and its length as a parameter and will return an array. That is the length of the original one. All right. So let's go ahead and write this dude. All right, so we are building a brand new array. So that means we're going to build a new array that has this length. So we'll say int reversed array with length, like that. And now we want to walk this array in reverse, adding those elements to this array forwards, because we're going to be building this array as the reversed version of this one. So for int I is equal to length minus 1. So that is the last legal bucket in my array AR, just like strings. Keep going as long as I is greater than or equal to 0. Decrement I each time. So I here is going to take us on a voyage from the end of AR towards the beginning of AR. Now, what I want to do here, though, is I want to put inside a reversed array, for instance, the element at length minus 1 in AR, I want to put at bucket 0 in reversed array, so on and so forth. So I'm going to keep track of an extra variable. You can actually, I'll show you how you can put it in the for loop here in a second. But we're just going to create another variable here called pause. So what I'll say is reversed array at bucket pause is equal to AR at bucket I. Make sure we increment pause. Now you could have done some crazy math thing and try to figure out how to work with AR or try to work with I to get you back to the beginning of the other guy, but you didn't have to. You could just create a second variable and use this guy to count up and the other guy to count down. Now, when all is said and done here, our goal was not to display the array, but to return that new array that is the original in reverse. So we will return our reversed array. All right, now we already have a function called display array. So we started off here. I'll just make this thing a little shorter so we can view it easier. So we have our array size 10. We'll build our original array. We went through and we filled it up with random numbers. We displayed it. Now we're going to call reverse array, passing it our array and our array size. And this guy is going to return for us a new array. Now I could just immediately pass that array to display array, or I could put it inside of a variable. So I could say int answer is equal to reverse array. And then I can go ahead and say display array answer and array size. Who's it complaining here? Oh, well, so that's actually, so the issue here is that syntax receive, this is actually a newer syntax saying return an int array called AR. So this will run, you pass that error message. Same thing in the other one. Yeah, same function. Well, I'll show you the fix for it.
Accessibility shortcuts.
So we'll look at the other thing here. So the fix for this is to return a pointer, the memory address of that array. We talked about arrays living in memory. So this guy would also be an int pointer. Still got it in the other place. So this guy is going to return an int pointer. And there's 10 elements, right? Well, I am. I'm calling displayed array. Or did I not call display array on it? Yeah, I did. So here's my first display array. Let's put some asterisks. Yeah, the second array is not being reversed right. It takes in an array, fills it up. It's got to be this int pointer because this is coming out as an int array. So let me use the syntax this guy wants. I should be able to say int array is my return type here. Why isn't it letting me use an int array as my return type? Well, I changed it to an int array is the return type, but an int pointer is the, this is having to do with older versus newer versions of C++. So an array is a pointer, so returning a pointer should be fine. But here, we can test this real quick just to make sure our logic is right. I'll make this guy void for a second, so it won't return anything. And then we'll go ahead and print out reversed array with length. Oh, I need to, this is line 32. I need to not capture the answer since it's a void value now. And then we're not going to display it out there since I'm displaying it on the inside. So here's my original array. And then here's my reversed array with the last guy first, so on and so forth, and the first guy last in my reversed. All right, so our logic is reversing it correctly. The issue is the syntax for returning that array. I don't want reverse array to return nothing and display inside. This is that idea of returning a value versus displaying a value. I want this guy to return that array. So I want it to return an int array, which we would typically say is an int pointer, the address to an int. That's another function I wrote right here. Yeah, that we wrote that. All right, so we want to return our reversed array, which is this array we built up here. And arrays are memory addresses. We looked at that inside of Keynote. Go ahead. Yeah, this is my local variable I created. Yeah, you might not like that I named it too closely, but yeah, this is the name of the array that I'm building my answer in. This is the name of the function. They just happen to be very similar. All right, so this guy's going to return an int pointer. I'm going to write it this way, and then we'll figure out how to get it to work that way. So this guy's going to return an int pointer. And I just want to see out reversed array. Make sure we're getting the pointer there. And up here, we'll say int pointer answer is equal to that guy. And I'll go ahead and just do a see out on answer, make sure they're the same memory address. That'll show that we are returning the beginning of that guy. But if you remember last time we looked at the Getting the length of an array. This is why we're passing around length in here. We saw a function called size of that told us how many elements are in an array. And it worked for arrays that were built like this, but it doesn't work for arrays built with where we allocate memory ourselves. And I think we'll see this here in a second. So let me do this. Let's just make sure the memory address is the same. So I'll call reverse array, passing it the array I want to reverse and its size. It's going to spit back an integer pointer. Pointers are variables capable of holding memory addresses. This guy will take in that array and the length. It'll go and reverse it. We've already seen that this logic does what we want it to do. And then I'm going to go ahead and just print out the memory address associated with reverse array here, reversed array. And then I'll go ahead and return reversed array, which is a memory address. I'll catch it right here in my variable answer, and then I'll print it out. So we should have the same memory address twice as our output there. Yeah, see, that's what's different there is the 0. And it's because of this syntax we're using for creating our array. I think what we can do here is we can say int pointer reversed array is equal to a new int array of size length. And then we get the same. This is actually a pretty interesting problem that I did not consider when I gave this. And now you'll see that but it's very related to what we're going to talk about today. So is what it is. So I'll grade the assignment easily because I technically didn't give you what you needed to do everything. But I also didn't get any questions on the assignment, so it's that too. But it's fine. All right, so let's talk through this for a second. All right, we already saw what this logic does. This reverses an array. And this printout is this guy right here. This printout is this guy right here. We notice that they're the same memory address. Go ahead. Oh, yeah, so you hate that part. Okay. Okay, here, how about this? Yeah, so all I did, I still did the random numbers. I just modded it by 10 to give me values between 0 and 9. Yeah. Yeah, so we're good with this guy's the original and this guy's the reverse of that. Okay, but right now we're focusing on these two lines here, the crazy memory address things. All right, so I passed my array in here, my original array that I filled up with numbers between 0 and 9, as well as its length. I built a brand new array here, but I built this array differently. The way we built it before is I had an int reverse array length, like this. These two lines attempt to do the same thing, but there is a difference here. This guy gets global memory. This guy gets memory that dies at the end of this function. That's our issue right here. When I use this syntax for that guy, what I'm doing is I am saying, oh, go ahead and get me enough memory to hold this many of these guys. Now, a couple of classes ago, I'll show you in our slides, we talked about scoping rules, right? So we talked about that whenever we have separate functions, those separate functions, they get their own scope, their own place in memory where their variables live. And we look for those things when we're trying to resolve a variable, we look in that memory location for those variables before we go and check at the more global place. Now, what this implies in our code here is that when reverse array was born, it got a brand new chunk of memory that was only going to survive so long as reverse array was still running. When I used this version of the code and then I ran it, we saw that we got these memory addresses no longer matched. The memory address associated with reversed array that I returned here became a 0. Why? I mean, he was not a 0 in here because I printed out reversed array right here, didn't I? So right before I returned it, I printed it out and it looks completely legit right there. Everything's good. My very next line is I returned it, presumably returning this thing. I caught it right here, and then I immediately tried to print it out again. Not a whole lot happened between these two lines. But what did occur is that new memory, that scope that was born with this reverse array, that guy died. Which means that any memory that had been requested from it was also dead. So that memory address is no longer a valid memory address. So those variables were reclaimed by the operating system and reset to their base values. All right, now, if the only thing I change here is the way in which I'm asking for memory, and I'll show this to you in a different way here in a second as well. If that's the only line I change, I'm just building my array differently. And instead, I'm using this new keyword. Let me show you the new keyword here. So we might as well now insert it ahead of the homework assignment since that's really where it should have been. So the new keyword is like our real estate agent. Its job is to go and ask the OS for an amount of contiguous memory to accomplish something. So in this particular case, if I say int pointer AR is equal to a new int array of size 10. When I build new memory, this guy is going to ask for memory. I just said that the new keyword is a real estate agent whose job it is to go out and talk to the operating system and find memory. That's his job. Okay. So when he finds memory, he's going to return the base address of that memory. And what kind of variable do I need to hold addresses? I need a pointer. So this guy is going to return the address where the base address of where 10 ints or can live in memory. I will store that inside of this variable named AR. Okay. So that's what that new keyword does. So AR now holds the base memory address of the contiguous chunk of memory that new found for us. This memory was found in global memory, not local scope memory. This creates a local array that will have its memory reclaimed when the scope which contains it ends, or so let's say dies. All right, so that's the difference of what's going on there. So if we go back to the code now, just to reinforce these words into output, and we just did this, but I'm going to do it again. When I ask for global memory, print out that value, and then return that value. When this scope ended, that memory survived because it was global. Go ahead. Yes. Yeah, and that's across all languages. So the new keyword is something you're going to see for the rest of your programming career. I'm going to show you a scarier version of new, the guy that came before new in a second, called malloc, memory allocate. But he effectively does the same thing. But yeah, so whenever at this point, when we're using one of these words that say, go get me some memory, that guy is operating off your actual computer system memory. Whereas this dude, it might look like it's a shortcut for this. And as long as we're only using this guy inside of this code, he is a shortcut for that. But this only got memory from our local scoped memory. And as soon as this scope died, all that memory was given back to the OS. Go ahead. Well, so you're saying, could I now access that variable up here? Is that what you're asking? Can I do something like like that? No. So and it's a really good question. So we're talking about two different globals. One is the memory. So we have our big system memory, your 4 gigabytes of RAM, 8 gigabytes of RAM, that guy. When we use new, we're asking for a location in that global memory. All right, that is a location that will remain alive whenever this local scope dies. So the memory remains alive, but the accessibility of the variable is different. So when we talk about variable scope, that's what this slide was about. This is saying, hey, when I'm in either main or check scope, I have access to all of these global variables. But if I'm in check scope, I don't have access to main's variables. And similar in this case, if I'm in main, I don't have access to reverse arrays variables. All right, so two different things. One is the scope of a variable, where do we have access to a variable? And the second one is when I request land, when I request memory from the operating system, if I use this, what seems to be, I usually refer to stuff like this as syntactic sugar. What seems to be shorthand for this line above it, they actually are doing two very slightly different things. This first one says, go to my 8 gigabytes of RAM, the big pool of memory, and find me a plot of land for this because I'm going to be using this memory at other places in my program. This guy says, I just need an array real quick in local memory. And when I'm done with it, I'm going to go ahead and clean it up. Or clean it up for me, because I'm going to show you the alternate side to that. One thing we could have done here, actually it wouldn't have worked here. I can say delete reversed array. So this is a function built into C++. This says, go ahead and give that memory back. I'm thinking this is going to probably give us an error because it doesn't like me deleting something that, actually this is giving me a different, because I'm returning a void pointer now. But in any case, this would give me the same thing as before, where the what it's actually doing is this guy. But that's going to say we can never reach that line. Yeah. Because this return makes a function immediately end. Whereas I have a line after that return that will never get hit. But maybe we can say the difference between these two is this. In this case, I'm asking for memory, and I'm going to rely on the operating system to go ahead and clean it up for me when this scope dies. In this case, I'm saying, okay, I'm going to make my own mess. When I'm done with it, I'll clean it up. So, and actually the error we have right now is this guy. So if I came up here and I say delete answer, and then I do C out on answer, I think it'll let me get away with this. I should get a 0 at the end. Yeah, it gets memory that dies. Let's see.
No, it's the select either 43 or 42. Yeah.
Oh, I get it. So we're going to leave it as that global one then. Yeah, see, it kept it when I deleted it out there because it was already a local variable of it. So I'm not going to be able to mimic what it's doing. So we'll just globally right now say, when you create memory like this, it is then ultimately your responsibility to give that memory back. When you make a mess, it's your job to clean it up. When you're done, when you're done. Okay, you make lunch, make a big mess. After you're done eating your lunch, you clean up the mess. All right. So when I'm done, when I ask for new memory here, when I'm done using that array, presumably here at the end of my program up here, I'm saying I no longer need this memory. Operating system, you can have it back. You can reclaim it. The reality is that when this program finishes running, our modern day operating systems will automatically reclaim the memory associated with that. But a good programmer, good programming practice would say, if I made a mess, I should clean it up rather than rely on, in Java, it's called automatic garbage collection. Modern operating systems, it's just clean memory is what they do. Go ahead. No, you actually can't. This exact, in Java, you'd write this way. So Java, you can manipulate memory. You just don't have the specific syntax for it. So that line of code there is Java. But you don't have a way of manipulating it afterwards. Yeah, you can still create it. New memory gets created all over the place in Java. Guys, that's question 1.
Yeah. Question 2, can you solve the issue as it's done?
Yes, but that's bad programming practice. Yeah, so what he's saying is, hey, but let's do it for your example. We can come up here and we can say we're going to make a int actually, let's just call it well, no, we'll call it reversed array. Although we don't have array size up here, but to mimic it, we'll go ahead and move our array size global. And then when we build this guy, we'll make him global. So now this array exists at the global level in our program. So then down here, we won't do any of those because we already have a global variable called reversed array that we just defined up here. So we'll go ahead and fill it up, do all our stuff. Now, realistically, though, I didn't actually have to return it. Right? I am returning it to main, but main actually already had access to it because of where I defined it, but I'm allowed to return it. So I will return it here. And we are then printing out that memory address. Which one is that? 49. Reversed array. It did make it. Saying it doesn't know about that. So this is a global variable called reversed array of size AR size. And it says it doesn't know about it. I wonder if I can't use this special syntax in the global scope. Because I should be able to do this. Let's just make sure that is the case before I advertise it as the case. Yeah, that is the case. So that syntax, that guy right there, only is allowed inside of a function scope. I can't do it at a global scope, which then makes the answer to your question, no, it won't fix it because I can't do it that way. It won't let me define this variable like this and then use it down here. It says it hasn't seen it before. So I'm trying to call it reversed array here. Presumably I defined it up here globally, but it doesn't know about it when I get down there. This guy. Yeah, it's not declared in the scope. So I would say this is globally declared. It doesn't see it when I'm in here. So since it doesn't see it, clearly that syntax doesn't actually declare something that's available globally. Now, I might make the argument, this argument, so we don't have this confusion moving forward, is maybe never use this syntax. Because this syntax is very special, is a very special case. Only when you need a function that you're going to go ahead and allow that memory to be reclaimed automatically at the end of the function. It's only for local purposes should you use this shorthand syntax. This shorthand syntax is not the same thing as saying reversed array is equal to new int array AR size. Even though these guys ultimately accomplish a chunk of memory big enough to hold 10 of these guys, they are doing it in different ways. And this guy will die at times that you might not want it to die or may not be accessible, where this will always work. But this comes with a consequence of you should be cleaning up memory that you requested, even though you actually don't have to because the operating system will do it for you. But you should do it. All right, so what was the third question? No, maybe we covered it in there. Was it? Oh, and it pops back up. Just okay. So let's go back down to put it back the way we had it. Then we'll go ahead and build it. So here, I just want to do it again so we can see what we were talking about with that array thing or with that pointer thing. Since I'm using this syntax at the end of this function, the memory that was allocated to this guy dies. Come on. So that's where we see the C out right here. Gave us that guy. but then this function ended. So the C out right there gave us a 0, showing us that that memory has been deleted. It was reclaimed without our consent because of the way we built this array. If we had instead directly requested global memory using the new keyword, which I think we could probably safely say we should always do now, we're going to always ask for memory that we want rather than relying on shortcuts. And in that case, now making only that change, it did still return it, right? Where's my reverse array? Oh, I'm not calling my reverse. Oh, yes, I am. Reverse array gets answer, print out answer. Inside here, am I not calling reverse array? Oh, there it is. I just wasn't scrolling up. So there's the two memory addresses. Go ahead.
It's not the base code.
Okay.
But, so the function that we created called
Mm-hmm.
has the. So what we're doing is we're going through we get this memory address somewhere in and then at that memory address we build these 10 values and we return that memory address.
Yep.
We go up and we call the base memory address. And it's print out going through this 0 to 9 what they describe.
Yes. So let's talk through that. So what's happening here is inside a reverse array, we are creating a new place in memory capable of holding 10 integers, global memory. Then we're filling it up with 10 integers, which happens to be the 10 integers stored in here in reverse. Okay, so we are putting at this global memory those 10 numbers in reverse. Then we are returning that memory address. We are letting somebody else know where they can find our 10 reverse numbers. So this memory address comes flying out of reverse array because this guy will return an int pointer. This comes flying out of here. I'm catching it inside of a variable called answer, which is capable of holding a memory address. So after this line, answer holds that same memory address that was inside a reverse array. And here's our evidence of that. This was printed inside a reverse array. This is printed inside of main. And it's because we handed off that memory address. We created it inside of reverse array, but then we returned it to main, and main proved that, I still know where to find it up there. Then we took that memory address, the one stored in answer, and we passed it to display array. Display array takes in a memory address. Now, the cleaner way of saying this, I mean, doing it like this is fine because this isn't where I'm defining it. But we could say int pointer LOL here, and it would still work because that's the base address of an array in this case. But I think the way we had it written here is not a dangerous way because this isn't when we're creating memory. This is just us saying, hey, give me memory. And that's what a int array does. That's what an int array holds. An int array is an integer pointer. And then go through that guy and display the contents of it. All right, so we called reverse, Reverse created a memory location, filled that memory location, handed that memory location back to main. Main then took that memory location, handed it to this display array, who then went through and printed it out. So we just handed around addresses. Okay. So questions on that? Make some sense? So that's why these two numbers are the same. This is inside of reverse. This is inside of main, proving that that memory address survived the end of this scope because we had requested it from global memory, but realistically, we should probably never use this syntax because this syntax has that side effect of basically you're saying you're only safe to use this syntax if you're doing everything local. The second you're going off to something else, you got to dump this syntax because you want that memory address to survive. All right. So now I'm going to talk about a concept called this variable passing. So we could say pass by value versus pass by address. We've been experiencing this pass by address thing. Okay. Pass by value means we are sending a copy of a value into a function. So any changes we make to that copy will only last as long as that function lasts. When the function ends, the value of the original will remain. Pass by address, I'm going to steal the words from up there. We are sending a pointer to a value into a function. So any changes we make to that memory location will persist beyond the end of the function. When the function ends, the value of the original will be changed. A lot of times it's referred to as no side effect versus side effect. And we'll look at this through a couple of examples here. We'll keep it as simple examples first, and then we'll apply it to arrays. Okay, so we're gonna have a function here called change by value. That's gonna take an int a as a parameter. We're gonna have another function called change by address, and this guy is gonna take a pointer to an integer as a parameter. I'll go ahead and implement these guys down here. Change by value. What he's going to do initially is he's going to print out the value he was handed. Then he'll change it to 121 just because. He'll print it out again. And then that function ends. This other function will do something very similar, except he's going to say print out the value at that memory location, then change the value at that memory location to 121, then print out the value at that memory location. So these guys effectively are doing the different thing, same thing, but the difference is up here we're working with a value. And here we're working with an address. Okay, so just put a comment here. This is pass by value. This is pass by address. Go ahead. The memory address. Yeah, this won't fly. Yep, but you're absolutely right. If I see out A here, A, the value of A is a memory address. Variables resolve to their value. The value of A is a memory address. The value of star A is the value at that memory address. Okay, so largely when we look at these guys basically do the same thing, right? The only difference is whether or not we're working directly with a value or working with a value that lives at an address. All right, we're all good with that. Let's see, before I change anything on here, we'll leave those couple new functions in this row, but let me write this code or put this code on Slack so you have the current version of things. Oh, and also in case you didn't see it, tomorrow night, was it at 5 p.m. I think, is the Acuity Tech Talk. It's actually on Zoom this time. Acuity is up in Sheboygan. They're one of our top employers. Super strongly encourage you to go to that. There's also a very interesting talk. I don't know if I put it in general yet, but on next Monday at 4 p.m. over in the Collaboratorium, there's a pretty famous guy in the tech space giving a talk as part of a larger symposium that's on campus that day. There's other talks that day that are interesting. I'll put up the whole thing for it, but that particular talk, the one from 4 to 5 p.m. is very, very, very interesting. And I think very related to computer science. So if you are around on Monday at 4 p.m., I would strongly encourage you to take a look at that. And I'm putting this up on Slack. Code for reversing array in global memory. Okay, so back to this pass by value versus pass by address. Now, inside of this function, we're taking in a value A, we're printing out that value, which we presume will be whatever the value that was passed in was. We're changing the value, we're printing it out again, which we presume will be now 121. See, and then this function ends. Right here, we take in a memory address, we print out the value at that memory address, presumably it's going to be whatever value that was passed in. We are changing the value that lives at that memory address, and then we're printing out the value of that memory address, printing out 121. So both of these guys should have the same output. The question is what side effect will this have relative to this have once these functions end? That is, what happens to A in the place that called this function when it ends? We'll say here, what happens to star A in the place that called this function when this function ends? So I'll go back in here to main. I'm just going to take out my display array stuff. So we can just focus on this aspect. So I'm going to create an int A is equal to 5. And we'll do a cout A. That's going to print out a 5. We're all good with that? All right. There's our 5. Then I'm going to go ahead and call change by value, passing it the A. And we know change by value will print out the value I passed in, which is going to be a 5. It then changes that value to 121. prints it out again, it's 121, then that function ends. I'll then print out A again. So the question is what side effect did change by value have? When I passed A in here, we did some stuff to it, including changed its value. Then this function ended. What will A be here? Will it be the original value of 5 or will it be the 121? In this case, it's going to be that original value of 5. So there's my original 5. There's the 5 inside of change by value. Then we change the value to 121. So there's the A inside of change by value after we change the value. Then that function ended. And now we're at that, my highlighted line here. What's the current value of A? We see that that had no side effect. Make sense? Now, if I call change by address, and I'm not going to pass it A. A is an integer, right? Instead, I'm going to pass it the address of A. This is where you can find A in memory, is the address of A. Okay? Now we see that did have side effect. I didn't hand it a copy of the value like I did the first time. I told it where it could find that value in actual memory. So any changes that happen inside of change by address were made to a place in global memory, not to a copy of the variable that was sent in. That make sense? Now it's going to scream at me if I pass in A here, because A is an int. That guy is expecting a memory address. Conversion of int to an int pointer, not allowed. Doesn't make sense. Don't give me a number when I asked for the address where a number lives. All right, that makes some sense. Now notice in both of these that these functions did not return a value. And that's especially interesting in the second one, the change by address. I passed in something that was modified inside that function. I did not return it, but I was still able to experience that change outside of that function because I changed it in memory. Main is accessing that place in memory. Change by address is also accessing that place in memory. And when change by address dies, that place in memory is still accessible through our variable A. So I'm printing out that exact same value that we had before. Okay, because I'm grabbing it from the same place in memory. I didn't lose, this is why it's called a pointer. I'm pointing to a place in memory. And in this case, we had two different parts of our program, both pointing to the exact same location in memory. Okay, and even though one of the pointers died off when change by address ended, the other pointer persisted, so we didn't lose access to that guy we were making changes to. Now, the idea here is that anytime we're passing in a memory address, we are passing by address. Whether that's a memory address to an int or whether that's the memory address to an array. Does that make sense? So as an example, here's my array with 10 numbers in it. I'll go ahead and display those 10 numbers. Then I'll go ahead and display my split thing here. Now I'm going to call my reverse array here, but I'm going to instead, so if we were going to change the kind of the wording of the assignment, instead of saying create a new array that it holds the reverse of the original one and return it, I'm now saying reverse the original array in place. And since I'm changing it in memory, it'll now be a permanent change. So I don't have an answer to display, but instead, I'll just display my original array again. Display it once, presumably in random order, reverse it in the memory location, then display it again, proving that it was reversed, but I didn't need to catch that value being fired out of here because that change was made in memory. Okay, so now we got to go and doctor up our function a little bit. So reverse array now is going to take in the same stuff. We will go ahead and reverse our array the exact same way we did before, but this guy's no longer going to return an int pointer. It's going to return nothing. I need to make sure I make that true up here. So now he's going to return nothing. So I'll no longer return here. I'll go ahead and not print out my memory address. So when I get to this line right here, reversed array holds the contents of AR in reverse. I now need to copy those contents back over AR because I want to make it change in the original memory location. For int I is equal to 0. I is less than length, I plus plus, AR at bucket I is equal to reversed array at bucket I. Okay, I never returned anything from this function. All I did was take in an original array. I made a new array of the same size. I went through and I filled that array up with the reversed version of AR. Then I went back through and I copied the reverse version over the old contents of AR. Now, this would be our example where I said, now we could, in this particular case, we could have made our, well, here, we could have done our reversed array like that. That would have worked in this case because I did not rely on the memory address of reversed array outside of this. I only needed it so long as this function was still running. But you never have to rely on that knowledge because I'm saying if you always use this syntax, you always ask for new memory, but you will then operate as a good programmer. You say, I made a mess. I now need to clean up that mess. So down here at the end, after I'm done using reverse array, I'll just delete reversed array. Give that memory back to the operating system. I'm done using it. I made the mess. I cleaned up the mess. And we'll see back out here that we'll have our original random array, then some asterisks. We'll call a reverse array, which doesn't return anything. It ultimately changes that array in memory. And then I'll display it again, seeing that now it has changed. Remember, these guys here are our, that's the new stuff we had. But so here's our 0, kind of bad luck there. 025, 025, it's reversed. All right, and we can see that this still would have worked if I would have used this other version of this guy. I would no longer need to delete it. It wouldn't have hurt to delete it. It would just be getting deleted twice.
Did you have to,
Actually, yeah. The second time it went to try to delete it, it said, that guy's not a pointer to anything, because we already had deleted it ourselves. So when the system went to clean it up for us, it was ticked off because like, look, you told me to clean up that mess, but you already cleaned it up. I just wasted my time walking up here. So in that case, we would just not clean up the mess. And then I won't scream about that anymore. So we get the same result. And the reason we got the same result is we did not rely on us returning that memory address from this function, knowing that that guy's going to get cleaned up by garbage collection at the end of this. But I would say that you're always safe to build your arrays this way. How am I missing a return? What does this guy say you should return? Yep. And that's kind of the whole point of this, right? This is pass by address. Pass by address means I'm giving you a memory address. Presumably you're going to make some changes to that guy. And then you're just done. Now, you could still return a value if you wanted to. Maybe you have a different value you want to return from here. Maybe you want to return the number of things you changed or something like that. What, just say return?
Yeah.
Well, that's not going to hurt anything,
Gotcha.
but that automatically happens when you get to this line.
Yeah.
Function ends of what does return do? Return makes a function end. So this would be good programming practice to define it like this and delete it when we're done, but we can leave our messes for somebody else to have their problem and it's not going to scream at us. And it probably would have cleaned it up when the program ended. But I would still say it's a good programming practice to, especially given the reason why we're using C++ in here, to kind of keep ourselves frustrated with this memory, with this pointer stuff. So that in the next class, when we go on to Java and we see a language that, or even looking at a language like Python, neither of these languages make us deal with that memory. The memory is still there. The exact same truths are there, but we don't have to make that distinction ourselves. It just kind of happens. Go ahead. Yes, but it's passed by address because we're passing it an address. Whether we're dealing with an array like we are here, or whether we're dealing with a address of an integer like we are here. We're passing an address. If I gave any of you the address to my house and you went and spray painted my garage, I'm going to be in for a surprise when I get home. As opposed to getting a copy of my house, you spray paint the garage on that, I'm not going to notice the difference when I get to my house. Correct. AR here is a address. I'm passing it. And actually, even in the way we've written this guy, it is working. This is actually interesting. When I passed in AR to display array or to reverse array, for example, why did it work? When I used that, we'll call it for the moment, the bad syntax for creating our arrays. Go ahead. Yeah, main has not died yet. I defined this guy inside of main. So that memory was created as so long as main was alive. All this crap is happening while main is still cooking. That memory address did not disappear till I got to the end of this guy. I would still, though, in hindsight, say we're going to create integer pointers. AR is equal to a new integer array AR size. It will still work, and this removes that question about whether or not the memory gets reclaimed or not. All right, and then in our last minute here, I did promise that I would show you, we could say int pointer AR is equal to malloc AR size times size of int. This might be in standing out, it worked. So these two lines do the same thing. This is using our new keyword I mentioned as our real estate agent, go find some memory for us. That guy is doing the same thing as this. Memory allocate this much memory in bytes. That is the number of things I want to store times the size of each of those things. This will boil down to something called a void pointer, which is a pointer to generic memory. I want it to behave like an integer pointer so that when I go to bucket 3, I took 3 integer size steps to get to bucket 3. All right. So this looks scarier. This would be very much old C syntax. So you never have to use that. This should probably be our preferred array syntax moving forward. All right, questions, comments, concerns, bribes? Go ahead. And we're done if you guys want to back up and stuff. Go ahead. So you want to pass in an array, but you don't want it to be changeable. Yeah, so that becomes interesting. You want to have an array, but you want to pass it by value. What you would need to do is you would most of our modern languages have a function built into it called clone, which allows you to duplicate a memory location. In here, I don't think there probably is one written as a third-party thing from C++, but you would probably write a function yourself, maybe called clone, that you pass the pointer into. It created a new array, copied the contents over, and spit out that new address. No. Yeah, you cannot pass an array in by value directly.
I was never able to turn in that last quiz.
Okay, did you email me? I don't remember.
I messaged you on Slack.
Okay, why don't you send me an email
Just this, or-
with that?
Okay.
Yeah, and I'll go back and I'll update the grade. What, the code I just wrote? I can.
Awesome.
Yep. Take care.
So question 3 on that quiz. I thought I was giving you an address.
Well, here, I can, give me a second. I can look up what you actually wrote.
Okay.